Yes, good evening. We'll wait for some time. Let other join, then we'll start the session. Yes, good evening. Any doubt is there? From last class or till last class? We'll wait. It's a 5-3 now. We'll wait for some more around 5 minutes. Then we'll start the session. Shut down everything. Good evening, everyone. Um, my name is MD Asid Raza, and I am PMRF scholar in the Department of Mechanical Engineering at Energy Trichapalli. And today we are going to have the week 3, the live session for the introduction to machine learning. Uh, and we have started just brief of the machine learning, where it going to useful, then how we can maximize that, like now the machine learning and all. And then we have started with the very basic machine learning tool. It's called machine learning. Like it's like a decision tree. It's a classification technique, and then we move forward little bit of regression technique. In that also we have seen that the linear regression and multiple linear regression. We didn't see the polynomial fit and all. That also will, if time permit, we'll see around also like that also we'll see. So before starting to the session, I want to ask any like doubt that you want me to clarify, or anything is there that you can ask me now. Then we'll start the session. Like we'll solve some. We'll take code of that decision tree, then linear regression, or maybe we'll take for the multiple linear regression also, and then we'll go ahead with the polynomial also, and then we'll see the decision tree also how it works, on which parameter it will going to work it out and all. As we know, for the decision tree we have seen the entropy, gene information, and then index, gene index, and then we have seen the gain also. In the similar way, in for the regressions also we have the different evaluation parameters are there, we have the that's called error, or maybe that will be having a slope also. Then Pearson, that the Pearson coefficient will be there. So that's all we'll think about that. And then as we discussed in the first class also, we were having like before entering into the machine learning course full fledged, we have to we should have some that like background of the some sort of mathematics. In the mathematics also, we should have the background of the algebra. In algebra also we'll go specific to that, that will be having that the matrices, tensor, and some sort of optimization technique. It's like finding out the different first order differential, then second order differential to get the like that optimized value and all. Okay, so these are the things that we have discussed around and all, and then we were having, then we need some sort of some basics of that also, what I can say, uh, statistic also. And if you see that, you can find out that same course in the like that the YouTube channel, like earlier the live session was there also. Just 1 minute, sorry for that. हाँ अस्सलाम वालेकुम। तुम फोन कर रहे, अभी थोड़ा सा लेक्चर ले रहे थे। अब तुम फोन करते, ठीक है। हम्म, if you go to the playlist, currently what we are working on the introduction to the machine learning. That's what we uploaded the last 2 week video. Beforehand, we were there like a statistic for biomedical engineers. That's also going to use for. Okay, and in the last semester also we took the course on the machine learning for the engineering and science application. In that we went deep of the some of what I can say mathematics and all. Okay, so I think we can start the session now. It's already 5:10. Hopefully there'll be no doubt. I think let's still people are joining. Where we are, where we'll go to here. I think we'll see the how we'll proceed the lectures also. If you see the course outline. So in the first week, what we have seen that inductive biases and then cross validation, like why do we need evaluations and then types of the learning. We have seen the supervised machine learning, then unsupervised machine learning, semi-supervised learning, and then we were having self-supervised learning also was there. And then second class, what we have second week, what we have seen the linear regressions also we have seen. What is the purpose of linear regression? To fit the line or maybe do the predictions also. Then we were having the decision tree and overfitting also. Then we have seen the trade between the bias and variances also. And today mostly we'll be seeing instance-based learning, like user-based learning or item-based learning. We'll make some decision based on that also. Then we'll see the feature reduction techniques we'll be having. Why do we need to reduce the feature? What is the curse of the dimensionality and all? And will in that also we'll be having the PCA and LDA. That's called principal component analysis. Then LDA will be that linear discriminant analysis will be there. Beforehand, we'll be having the KNN also. KNN also, it's also to make the classification only, like it's not like a non-parametric and all. To and then we'll be having some sort of like filtering based method, like we can do the user based filtering, or maybe we can do the item based filtering. It's something like called the feature reductions itself. Yeah, if anyone have the doubts.
Good evening, sir. Sir, you
Yeah.
will not discuss entropy and information gain, gene impurity, all that. That is week two only, but
Look, do I need to
like
do
you
the
have gone ahead to week.
okay? Shall I go with that also? We'll take some
Discuss five
example.
minutes, just 5-10 minutes. Yeah, sir, 5-10 minutes might be.
Yeah, sure. Then shall we do it in the end or we'll do it now itself?
Sir, at the beginning only, because then we'll go to week three and four. And what I am asking is for week two.
Yeah, sure. Fine. We'll go with that also. No issue. We
Thank
were
you.
having that course also, like question number 7. We'll take one example. Actually, we were having question number 7. Yeah. Shall we go with this question then? It's actually to form out the decision tree. In that only we can solve all the entropy, like gene index, and then we can solve that gain also. So please just go through the question. What is the exactly is that? Then we'll go ahead with the solving also. So what we have is the we are having like that Martin. Just 1 minute. Then we have the humans are there. We have the two species are there. And based on the following features, what we have is the green. Then we'll be having the legs. Then we'll be having the height, and then smelly will be there. And we have to do the training of the data also. So which attribute will be the root of the decision tree? So this is the typical actual decision tree problem. So if we count the spaces, like what we have is the 1, 2, 3, 4, 5. So we'll go with that. Is 5. Then what we have the humans also. How much is there? 5. So first step like to how to get the entropy. formula, if you go to the basic, like it's called probability of that one species, and then log of 2
No.
into PM, like it's again like that the probability minus of probability of the second feature log 2 P of H. So this is the formula actually for the
But
entropy.
first one also has a minus, right? First one also has a minus, but
Yeah,
again minus P of
yeah, it will be the minus will be there. So what will be the probability of M? How many would total number of what we have is the 10. How can we get it? 5 by 10. It will
10.
be 0.5.
Right. Right. And log 2, log 0.5 base 2.
Yeah, this also 0.5. So now we can get the entropy minus of just 1 minute 0.5 log base 2 of 0.5 minus 0.5 log 2.5. Can you get the value of this? If I don't have the calculator here, just 1 minute, I'll save it.
So log 0.5 base 2 is minus 1.
So it will become entropy 0.5 minus 1 minus
Yes.
0.5
Minus.
minus 1.
Again
So
minus. Right.
entropy will be 1.
Right.
So now
This density. This
then we'll take the attribute.
So
First
sir, we
one,
do it for every column basically, right?
yeah. Actually, we have to do for
Okay.
first we have to do for the green, then legs, then height, then smelly. Then in that whichever will be having that gene index low, that will be the year that will be the that attribute for that particular that root of this entry. That the minimum.
But so this is not the way we are calculating Gini index. We are calculating entropy. So we will look for the highest entropy value because
Just
entropy is a measure of
first
disorder.
we'll go with the green. I mean that I'll just solve it.
Okay, sir. Okay, thank you.
So that's first is the green. In that, if we say that total number, how many that what we have? If we take the values, green, no, what we have, how much is there? 1,
So 4 yes.
2, 3, 4, 5, 6.
6.
Oh, 5 yes.
6, sir.
Yeah.
6, sir.
Okay.
Yeah. So what will be
No,
there?
no, no. 1, 2, 3. So we have 4 yes and 6 no.
Yeah. 4 yes, 6 no. So now what will go? We'll go with the again entropy. So first will be minus of 4 by 10 log 2 4 by 10 minus 6 by 10 log 2 6 6 by 10. Is it?
Yes, sir.
Then so we got some entropy value. Let's say it's point. How much will come for this?
Sir, 0.221.
Just 1 minute.
Sir, 0.221.
0.221. Then just one, like just 1 minute, just 1 minute. I think we went somewhere wrong. I'll just do it.
Sir, we are finding the information gain, which is equal to original entropy minus
Minus it
the
will be there.
attributes.
Yeah, just 1
Yes,
minute.
sir.
Just 1 minute. So first case will be that we'll take green is we'll take what? We'll be taking for the first
Sir, we will do 1 minus.
just 1 minute, just 1 minute. I'll solve it. Just I'll solve it. Don't worry. First we'll take for the Martian.
Your screen is not visible now.
Okay, just 1 minute. I think now it will be visible.
Yes.
Yeah, so in the case of that Martin, what we have the total M is equal to 5. Is it? And
The
green
screen is not visible.
still not visible?
Sir, it's visible.
So now it is visible for me. Now it is
Visible, sir.
Okay. So for the
No,
Martin,
sir, it's not visible.
it's not visible.
It is visible. Please log out and join once more. Might be
Yes,
it is
yes,
because of
yes.
the network.
Visible, sir. Screen is visible.
Okay. So in the case of green, like how many the sample will be there? In the case of that, like here, what we have that will take Martin, M is equal to 3. Green of Y total will take just 1 minute, just 1 minute. I just messed up with the total of no how many is that? 1, 2, no is having 2, yes having 3. Now we can find out the how much like now we can get the entropy. Okay. Sample yield 4, how come it came? 1, 2, 3, 4, 5, 2, 3. So now we'll get that into total number. How much like what we have is the 5. So 2 by 5 minus log of 2 by 5 minus 3 by 5 log 3 by 5. And then for the human, also 5 sample that what we have. In that also, how many that we have the no? 1, 2, 3, 4. So no is equal to 4, yes is equal to 1. So for this entropy, we'll be having minus 1 by 5 log 2 1 by 5 minus 4 by 5 log how much? 4 by 5. Is it? It's correct or not? Will we able to do it or not? Then after we can get information gain.
Sir, we have to find the entropy for all of the attributes and then
1
use the
minus
smallest value of entropy.
yeah 1 minus for this both attribute like for this entropy like for the case of green no minus green of yes, so we'll get 1 one information gain, is it? Similarly, we'll go for the all the cases, for the legs also, for the height also, for the smelly also. So if you see that that the like information that gain will once will get. So first case, for the case of green, will get one information gain. For the case of legs, second information gain. For the case of height, will get information gain 3. For the case of smelly, will get information gain 4. So whichever the information gain will be the having most value, so we'll take the root of the decision tree, is it? Just. So first we have to, for the like that the Martin, then the humans, then we'll calculate information gain. So that will be case for the green. Just see, like don't get the confused. We have the two species are there. Like it's the like that the Martian one, second one is the humans. In the Martian, the green have one, two value. Then the like that the case of no value. Then the yes will be having 3 value. So then we can calculate the corresponding entropy. Once we got the entropy, then we can calculate the information gain from the. So in that case, so then similarly we'll calculate for the humans also. Once we calculate the humans also, so we can get the information gain like 1 minus entropy of that case of like green no, in then the green yes, then we'll get the information gain. So similarly we'll go for, again we'll go for the legs, again we'll go for the heights, again we'll go for the smells. So whichever will be having that highest one, that will go with the case of what I can say that the root of this entry. I'll just show the formula also, that how it went. See how it's going here. Just one gene index and all. We kept the formula or not? I think it will be clear, or either still some doubts are there. Can anyone tell?
Clear, sir.
It's clear, na?
Yes, sir.
Yeah, we have to go. This is the manual way we can go. Today also some codes also, like we can do the fit tree, then we can get the direct tree also, we can get it out and all. So this was the case for the for the decision tree. So the first step is to find out the what I can say entropy. Once we got the entropy for the all attributes, then we can get the that information gain. Once we got the information gain, so we can calculate the Gini index, and then based upon the Gini index, we can make the which one will be having the root of the region tree.
Sir, only entropy won't be enough.
No. Entropy is just a parameter. So we have to get get the information gain also.
Okay.
Yeah. I think we can go ahead with the current week.
Yes. So right at the end, come once to slide number 97 of this PPT later on, after you are done with everything. So you
Okay.
teach, not an issue, later on.
Okay, fine. Okay, so we'll so the whole idea is that let's say we'll take one example. So, like suppose that the university student to predict whether the student will pass or fail based on the two factor. First one is the student that study hours say like per day, and then they have the attendance percentage also. So we have to find out like whether they'll pass or fail. So what we're going to take, we'll take a new student. They have the study hour of 3 hour like a 3.2 attendance of 76%, and we have some data set from the previous student. First uh, student, they have studied for the 1 hour and they have attendance of the 55%, they got fail. Second student, 1.5 hour, 60% attendance, they got fail. Again, like 2 hour, 65%, they got fail. 2.5, 70, fail. So similarly, we have the total of 12 number of data sets are there. Okay. So the thing is that like how we can we make it decision? So in the decision tree, they're going to sequence if then question, like if and then question. If less than 70%, 72% of the attendance, they're going to fail. If it is greater than of the 72%, so what will be the study hour? Let's say it's a 76% like is there. So I just took one like that quantified value. So I'll take 72%. Less than 22%, it got fail. So means like that we are going to stop it. Now, okay, they got the attendance percentage of that the greater than of 72%. So then the question will come, what was the study hour? Whether it was going to be a less than 3 hour, it's got fail. If it is going to be a like more than 3 hour, it got pass. So this is how we're going to make a tree. So the model will going to learn the rules are such a if attendance is low, they're going to fail it out. If attendance is sufficiently high, then the study hour I and like if study hours are high, it's going to pass it out. Okay. So what they will do what we will do actually first we're going to we'll go to the like that MATLAB and we'll see where is the decision tree here. What we're going to do, we have the decision tree classification. We're going to predict the student either pass and fail. It's a
Sir, how did you get to this? Sir, how did you get to this? Sorry, I interrupted this MATLAB thing. I had told you last year also you'll show how
sorry,
to
sorry.
like, sir, how did you go to this? I mean, this is not the Jupyter notebook or something. This is MATLAB. So
Yeah,
like,
it's
how do we install it, or it is like we can work in the browser directly? Like, I
yeah
mean,
that you can work in the browser also actually, and it's
okay,
actually free.
okay.
If you want to do it the standalone, so that going to be like commercial one, but that you can use the browser one. It is free actually.
And sir, what we work here that gets saved in the cloud.
That we can save it in the cloud. There is no much issue if you connect with the your OneDrive or something like. But
Okay,
web browser will not going to work in the cloud. That you can like save the locally.
okay, sir. I will just try right now in my browser. I'll type and see where it takes me.
Just see, like I'll be just explaining the code how it works. Similar way that you can do the coding in the like that the Python also. I'll just explain the what can be the steps, what are the fit parameters and all that will be there. Only here the that the syntax will be different. Their syntax will be the print or something that another syntax will be there, and then in the that the MATLAB will be having some different uh, interface, but fitting parameters and all that, like all hyperparameter will be same. Only the syntax or interface will be changed. So I'll just explain which fit I'm going to use or which tool like a tool that I'm going to use, and then what is the like mathematics behind of that. That's all. Okay. So I think with this that you can solve on the Jupyter also, like that the Python also, or in the MATLAB also, and that the meanwhile I'll put the code in the like drive folder so that you can access in the that access the code also. Okay. So I'll do one thing. First, we'll start with the CLC. Like it's a like we can like that clear the command window and then the workspace. Then we'll close all the unnecessary window also. This is the, like in the case of MATLAB actually. Like that's the basic thing we have to do once we're going to start any the like fresh project. So there should be no any other things should be in the workspace and all. Command window that depends upon like once we run it, then we can get something that other things that can come. But in our workspace, another parameter or the value should be not there. if it is having same source for the code also, so it might overlap, and then we can get the some error also. So once we are going to clean up with that, we are going to start like here we took one example, whatever that I shown in the like example I took from the book, and then we wrote like code, and then we can get even the code from the MATLAB AI also, that you can sometimes if you get the some error in the syntax, or maybe that like exceeding limit and so on, that you can change it and all. Okay. So the thing is that problem is that we have to predict the student pass or fail. So it's a discrete problem.
Sir,
It
please zoom it. Sir, please zoom the screen.
okay,
Code is
fine.
not visible. Correct. Thank you, sir.
Okay, thank you. I think like that the now will be fine.
Yes, sir.
Yes, sir.
Yes, sir. Thank you, sir.
Actually, this screen is 14-inch only, so and I do have the
So
some
we
bigger.
can zoom it.
Sir,
We can
now.
zoom it.
Sir,
We can
now
zoom
it
it
is
at our
visible.
end.
I think
Sir,
now it
it
is
is
We
fine.
can also
visible.
zoom it.
Sir, visible it is right now.
Okay,
Thank you,
okay,
sir.
okay. So before jumping into the coding, I'll just say one thing. Like we have to understand whether this problem is related to the classification or the regression. So the like that the problem what we have is the either the student will pass or fail. So there is no continuity. So it's a classification problem, is it?
Binary classification.
Binary
Yes, sir.
classification. Then after we have to see what are the features or what are the input parameter what we have to train the model. So the thing is that like now they are saying the student going to pass and fail. So if for that we have the two criteria. First one is the study hour. Second one what we have is the attendance. So this will call as a feature. It's like it's the representing the what we need to get the output and input. Okay. So this is the thing like we so now we understood the problem, that this is a classification problem. We have to we have the two feature. Based on that, we have to make some decision like how whether the for the particular case, if that student will study for the particular hour, and they have this much certain that attendance is there, whether they will pass or fail or not. This is a similar example like one in the last class someone have asked for that also, so that you can take this as a example, then so then you can implement in that also for your classroom also. Okay, so we'll go ahead. So the data set is uh, that is the input. So that is the first one is the one is the hour, 55 is the percentage of the attendance. So we have like two feature value we have given in the form of vector in the matrices that you can see here. One, then that 55, 1.5, 60. Then after then the target value what we have is the target value is the y. Either they're going to pass or fail. So that we also know that it's actually a decision tree is the supervised machine learning progress, like a process. So this is the x value. For the x, we have the two vector. That the two feature. So we got the like 1/2 vector. Like we got it. So this is the vector space. Then after, how many students are there total? It's around 40, 55. Yeah, fine. Then we'll be having the categorical value. It's a target value. X, we are going to map X to the Y. So now we know the input value. We know the output value also. Now the thing is that we'll see the visualize the data. It's like how to generate the figure. How to generate the figure. Once it's done, so we are going to scattering. GS scatter is there. So GS scatter, then X label, Y label. It's the fundamental things that you can do in the same uh, in the Python also. So then after we can draw the tree also. Then after plot the decision like a region also, zero point 0.5 into 300, like it's the like that the min max and all will be there. Once we'll go with this, we can predict also. Just I'll run the code. Just 1 minute. it's a fit tree model will be earlier for the decision tree. What we want to we have to go through the each feature attributes to find out the information and like a tree that entropy information gain, then the gene index we can get it. But here we can give the tree model. For that what we have is the fit C tree. Okay, so they're going to fit in the tree x to the y. They're going to this is going to map x to the y map. They will do so. It's like a single code. We will not we like instead of doing in the full that mathematical calculations and all, we can just type fit C tree in the MATLAB, and the same thing if you want to do in the Python. So here we can see X, the data will be there. We have the feature matrices that let's say we that the earlier was the that the number of hours, and second was the percentage of the attendance, and then Y was the target vector what we have to pass or fail. Here now we can do that the model will be the decision tree classifier max depth. Like from there here we have calculated like x train, y test will be there. Here we have done the splitting of the data we have split. That the training will be used for the 80% of the data will be going to use for the training, then 20% for the testing. That I'll explain in the coming and all. Then we can like that the model decision tree classifier, then their value will be there, then we can fix it out in the MATLAB. We have the single line code. It's called tree model fit. So now based on the like tree what we got, we can generate the tree also. View tree model modern graph. Then after plot decision like a region also, on what basis they took the decision also we can see around. Okay, and this is the whole thing to how we can get the better picture. This is actually for the plot actually. Then after, if we want to do the prediction, let's say if a student that we were having the data of how many data was there, I'll just show week 3. We were having the data of 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and this all data was there. So now I want to see if any student have the 3.2 hour and 72% of the attendance, what they will do, like whether they're going to pass or fail. Okay, so first we have to give the input like that. So that will be the new student 3.2 at the hour and 76. So this value was not in the training. Once we have done the training here, here we don't have the 3.2.
You are mute. Voice is not audible.
Sorry. I think it's now fine.
Yes, that's fine.
Yeah. So actually, this was data was used for the training. So now I want to see 3.2 hour and 76% of the attendance. So it's something unknown data. Now we are going to predict the whether so they're going to pass or fail. So this was the training. Once we did, done the training, so now the same thing can be used for the prediction. How we'll do it? Let's say if any student have studied for the 3.2 hour and attendance of 76%, what will be the like prediction? So once we'll run it, so for the case of new student 3.2 hour, 76% of the attendance they have passed. So now we'll check for the 1.2 hour and attendance of let's say 56%. This data is not actually in our data set. Now we are giving the new data set to do the training. So let's say what's happened with this. We'll run it. What happened in that case? They failed it. Why? Study hour 1.2 and then attendance that reason they have failed it. Okay, so this is how things will do. So once we have once we will have having the bunch number of the data that we can use for the training, then we can predict by giving the some set of that the new input and then output and all. Okay, so I think till here it's
Sir, sir,
yeah,
I have a question.
yeah,
Sir, this data which you are sharing,
yeah.
where is this data present? Is it in a CSV file? I mean, where is the originally data coming from?
This data actually
And
typed
how
it.
did you?
I typed it here, or if you want to type it in the Excel, that you can type it like here. I'll just show it to you. This data actually very less number of the data. So this is the input. Actually, this is typed here only.
Ah, right, I got your point. But suppose sir, there is a huge data set which is basically in a CSV or in a XLS file.
Yeah,
Now,
yeah,
how this file will get included here in this MATLAB? So
yeah,
from
yeah, yeah.
that file, how will I segregate X and Y? I mean, how will I separate my input features and this? I mean, in Python, it is done in a different way. And here, how do we do it? Like, what is the command that we give so that I
In
can segregate my output labels and input features?
yeah,
I mean,
that you
I
can do.
separate that X and
Hmm.
Y.
Yeah, yeah. Let's say I have I'll open the Excel sheet. And I'll just show one thing, like we have already data set is there. So let's say if this is the time case, one, this is the this is the whole input. This is the time, one parameter. Second one is the we have the muscles. Third one also we have the muscle. Fourth also we have the muscles. So one, two, three, and then corresponding will be going to label the fatigue. Okay, and some got non-fatigue. Okay, some got fatigue, some got so once you're going to load the data, once you're going to how you're going to load that code also it will it's called load CSV file or XLX file. That will be the code for the MATLAB. This is actually like if I'll go to explain to the that MATLAB code and all, it will go again very a very long process. So just I'll show the code itself directly. This is my actually the research work is that I don't want to show the code, but anyway, I'll just show it for a while. Just see here, file's name, fatigue dot extension. That what file name was there. If I'll show the file name, if I'm right, just see the file name, fatigue, like underbar. Then we have the leg extension. Then I have saved in the XLX like that XLSX file. Then the sheets will be there. Then the first like that the muscles name is there already. Then after how they are going to do it, that the that S is equal to that one is to length. That a sheet will be the first sheet, second sheet, third sheet. Like it will be the for the each subject. Let's say this is the I have total of 11 subjects are there. So that each like subject have some values are there. So this is actually a once you learn the MATLAB, then you will get to know that how to load the data, how to read the data and all. So I think that is not the our part for now. If you want to learn it, then we have some like that you in the YouTube or some books are there that you can go and find out. Is it fine?
Okay, sir.
Yes, sir. Thank you.
Yeah. So I think we can go back to the our own code. Where we were. Here we are not there. Regression. Yeah, here only we are there. We were there in the decision tree. So here, what was there? I took very short number of data, 12 data only there. But if we if we have some data of 10,000, 1 lakh and all, in that case, either we can give the text file or maybe that CSV file or maybe the XLS file that you can give it out, and then we can do the commands. They are going to read the like carefully what will be the input, what is the output will be there. That will do. Once we are going to get the things, then we can fit the tree. Once we fit the tree, now the our decision tree model is trained. Once the tree is got trained, so what we can do, we can predict the with the different students. Once we and so there is another way to do it. Like we can divide the data into the train is like a train and test evaluation. We can use the 70% of the data for the training, and then testing can be done for the 30% of the case. So in that case, through that, what we can get the confusion matrix like that. So training will be used for the like how the model was trained. Testing is used like something that was to get the that the like predicted value or the actual value. So training one will be going to be a predicted one. Then the actual value for the test case, it going to whatever we have taken the case for the testing. So in that case, we can get the decision tree. Then from there, we can calculate the accuracy, precision, recall F1 or maybe the ROC curves and all. We can get it out. Once we are done with that, so we can that even we can get the confusion matrix also, confusion chart, y test, y predicted. So this y predicted will be from the training case, y test data that will be getting from the here only. So this is how it's the fundamental part of the decision tree. So we'll be having a single line code to train the model if we don't divide the data into the training or testing. If we are going to do if we are going to do, then we can do through the we can do the partition that's called cross validation that we can do. 70% was used for the training, 30% was used for the testing and all. So this is the whole about the decision tree. I think the that the hopefully it's clear decision tree now. Fine. Shall we go to the next part?
Yes, sir.
Yes, sir.
This is the how they're going to take the decision like once they are going to 1 hour 55% attendance is going to fail. 1.5 60% is going to fail. 2 hour 65% it's going to fail. Then we are having to 2.5%, 2.5%, and then this value here it's going to 70% fail. But once it cross here 2.8 hour 2.8 hour 72% attendance, from here they're going to pass it. Okay, so even we can get if we have the bunch number of the data of any schools or any colleges and all, we can do the predictions. If any student will going to cross this threshold, they're going to pass, or either it's going to fail. So this is how the things will be pass percentage or fail percentage we can find out. So this is the again a classical example of the machine learning. Okay, so now we'll move forward to the, I think we'll be running out of time actually. Next, so what will be the something called advantage? It's easy to understand, easy to visualize, and what is the disadvantage? It's going to easily overfit. The thing is that they're going to sometimes bias also, or maybe the variance will be the too high, and then a small change in data can produce the a different tree. So it's actually a like a very classical machine learning technique, that the extension of this what we have is the random forest. So this also we'll see once we'll go to the like third or like fourth or fifth week, that also we'll see. So this is actually a very classical example, but in the case of random forest, we'll take instead of a single tree or individual tree, we'll take 100 tree or maybe that 10 tree or maybe 50 tree to get the best result from the data set and all. So now we'll come to the regression. Now the thing is that we'll come to the regression. What they're going to do, y is equal to mx plus c, some error will be there. Now the thing is that again we'll go with the similar example. Suppose a university like that want to estimate a student final examination score based on the number of hours studied. So earlier what we have used is it was the classical classification example. But now I want to find out what will be the regression. It's called to find out the actual marks. I am not going to decide whether they'll pass or fail, but it's actually a marks how much for that particular hours they will study, how much marks they will get it. So again we'll take some same data set. 1 hour they got like 42 marks. Earlier what was there? We were having the percentage of the attendance, we were having the number of the hours, and then categorized like whether it's going to pass or fail. But now it's the data what we have is the once I'll study for the 1 hour, and so they're going to get the 42 marks. 1.5 hour 48 marks, 2 hour 42 marks, and so on. Once they study for the 7 hour or 6.5 hour, we are getting somewhere around 93 marks. So now the question is that like we have to get the exact marks, not the category I want to find out and all. So if you see the classification output was the category, pass or fail, but here regression output is the number, like how much we'll get the exact number. So here what we'll do, we are going to find out the curve like this, or it can go it depends on the how good fit we are. Okay. So what will be the sum, like we'll be having to evaluate the model. This is mean, absolute error. Then this is called root mean square error. And this is actually a correlation coefficient is there. So now we'll go to the code. Again, similar way, I'll be not taking the any Excel code and all. Instead of that, I'll be like data set, I'll be having a very small set of data set. There's no much data set I'm taking for the examples actually. Okay. Whatever we took. So here the problem what we have is it's the problem that what we have is the linear regression. We are going to predict the actual marks from the study of the hour. We have the x is the input, like it's the x value one, and then we have the data set. What is the target value for the 1 hour? 42 marks. For the 2 hour or 1.5, we have the 48 marks and all. So now this is the x and y value. It's the like again a supervised machine learning problem. Then after we are going to fit the linear regression. So that for the fitting of the linear that the linear regression, we have the model called fit linear regression. For the similar case of Python also, instead of Bayesian tree, we can get for the regression also. Here we'll get the same thing. Model, linear regression, whatever the like either you have made it that the feature value or maybe the x trains like or x test, y train, y test value that you can give it here directly. Okay. So this is the case for the Python, and this is the case actually for the what I can say for the MATLAB case. Just type the model is equal to fit of lm for what, for x case, that x vector what we have, then the y vector we have, then we can display the model. They're going to display the model also. then we can plot the original data, how the data is looking like. So once for this we have done the scatter plot, x and y, 70 was the like their size, and then that is the field. Then x label we have given the study hours per day, y label is the exam score, title is that again we have taken same thing. Then we can plot the regression line also, that the x line, then the y line, it's called predicted one, how it came across. So we'll show the how it looked like actually. So how it looked like, this is the data actually. This is the data actually. Once they were studying for the 1 hour, they got for the 42 marks. Once they study for the 1.5 hour, they got 48 marks. This is how the things went. Then after second code, what we have is the how data was regression, like the regression, like it's a data got regretted, like it's a regression data. Okay, and we got the values also. Then after next code, what we'll having, we can do the again the new prediction. Again, I'm saying like we can get the, so now the training we have done for the how much? 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. So now I am going to do the training for the how much? 4.2 hour. Whether the is that the how much, that the how much hour, like that the how much marks they are going to get for this percentage, for this study hour. So for the 4.2 hour, we got the 72.75 marks. Okay. Then after, we can again check with the we can calculate the predicted one. Then we can calculate the residual. Residual is nothing like a actual y value minus of y of prediction. Residual is nothing. It's just a error. Is it? It's just a error actually. Residual. Then we can that. So then we can plot the residual also. This is how it will look like. This is how it will look like. This is the our baseline. Whether it's got positive, like this is the positive error, negative error. It can come like sometimes the y is more, sometimes the y like predicted y is the more. So either way it can go. There's no much issue will be there in that case. So now the second that the like that we can go for the next part. We can find out the actual how much mean absolute error is there. So absolute value of y minus y prediction. Then we can get the RMSE value. Then then we can get the R square value. So we can see here we have already calculated. MA is the 0.6, and then RMSE is the 0.686. R square value is the 0.998. So if any line is the fit or close to the 1, it's a very good fit. If it is going to close to 0, it means it's not a good fit. Like we have the huge amount of the error is there. Okay. Then after we can do the same thing, train and test. Earlier we have done the direct training. Now we can split the data in the training cases and then test cases. Here training was used for the 70% of the data was used for the training, and then testing was used for the how much, remaining 30%. And then based upon that we have calculated the predictions and all. In that case, we got the mean absolute error of 1.412. RMSE is the 1.572, and then R square 0.992. So it means here 70% of the data was used only used for the training, but in direct training we have done every data was used for the training also. Okay. So again, we can calculate the same, that the MA, RMSE, then the R square test. Then the second part can be our multiple linear regression. Earlier it was the study hour we got the marks. Now we'll be having study hour, attendance, and then previous exam score. Then we have to find out the regression line. So the thing is that only the input vector that the input vector length will change. So we can see here, study hour, this much number of that 1, 1.5, 2 and all. Attendance is actually the corresponding 55, 60, 65. Then the earlier score was the 40 and all. This is the final score. Means it's a final score means it's called target value. So now we can calculate the here it's we have randomly created. We didn't create in the forms of the vector or the matrices. So now here we can calculate the T table, study hour, attendance, previous score, and then final score. Then again we can fit the multiple regression. It's called like final score. Final score is going to target with the study hour plus attendance plus previous score. Okay. So once that our model is going to fit, we're going to display the model, how it will look like. Okay. Then we can see around here. Then the similar things we can do from the earlier cases also. So from the prediction, from the model, we can calculate the for the new student also. So here we can see here 72.64 and all. Then after one more thing will be there, we can check with the polynomial regression also. This is the case of what we have is the till now what we have is the y is equal to mx plus c or y is equal to beta plus beta 1 x1 plus beta 2 x2. It's a linear regression. Now we can check with the y is equal to alpha plus beta 1 square plus x1 beta 2 x1 no beta 1 x1 square beta 2 x2 square beta. This will be not the square actually. This is the coefficient. So this can't be square. This x value will be the only it go in the polynomial. It can go either second order, either it can go into the third order. It depends upon the our problem statement. So now we'll just see again we'll be having a x value, y values are there for the x corresponding y value that we have already. Then here is the second order. Anyone is the lobby? Still lobby. Someone is there. I think once like for that again entering we have like again we have to wait in the lobby. That let's say someone got out of the class, they want to re-enter. So whether it will be going to direct or if, that again I have to let enter. Like that the permissions are required.
So you
I
have
think so.
to
Required.
admit the child. Like your permission will be required.
Okay, I think there is a way to change for at least those who joined once. They if they are entering like second time, so we should not do like we'll there like something like that is there. No. Okay, I'll
So
check it
don't
out.
know, no idea.
Okay, I'll check it out that later. So here I'm going to check with the like second order model. So this is how it will look like. So this is going to create the polynomial model x2 like x square. Then we're going to fit the model in the case of this is the x second order. Earlier it was the x only. This is the whole was the x. Whole was the x. Then target was the y. But now x is there, but in the second order polynomial. Then we got like y the target. Then we can go. We are doing the same thing again. What we have done for the linear regressions also. So this is how it will look like. Observed data, polynomial data. We can calculate the RMS value, error value, and all. Let's say we'll check with the third order how it look like. This is how it looked like. So like second order fit was good. Second order fit was good comparatively. Let's go. We'll check with the first order. It's the linear. It's actually they've sent the warning. It's called a linear regression. This is how the linear regression look like. This also it's like some sort of we are not going to fit correctly on the straight line. If we check with the second order, it's actually fit it off. We can check with the third order. It's again get worse. if that even we can check for the fourth order. It's like getting worse. So sometimes the some data will be having that the lower order will not give the better results. So we have to keep increasing until we can get the best fit and all. But again, the question will be there up to what extent we can go. So this is again we have to check the nature of the data, how it look like, and then that we have to decide it up and all. So I think with this we have done with the regression. Now we'll go with the features and all. Okay. So again, we have seen that instance based like that learning that the last class. One way to solve task of approximity is to either discrete or then the real value target functions will be there. So it's either the classification or maybe the regression. For that we have the different that the models what we have. If not true, then we'll be not having the select. It's based on the similarity. If there is no similar input maps or something like outputs are there, so that the learning that the we have the learning will be the impossible. If it is true, then the learning that got reduced to the defining got the similar. So it means like something machine learning task is to mimic the human activity or that human activity. So that the things in this case also will go the instance based learning also. So in this also what will be having a it's called KNN, like based on the distance, based on the neighboring distance. Okay, and if you know the coordinate geometry, we have the Euclidean distance. That Euclidean distance will be there. We have the x1, y1, and second point what we have is the x2, y2. Let's say and this is the our like point one P point. This is the Q point. We have the x1 here, y1 here. We have the x2 here, y2 here. So we can get the distance between the 2 points by using the Euclidean distance. It's called x2 minus x1 whole square plus y2 minus y1 whole square. So that the whole KNN is based upon the Euclidean distance. Okay. So in that case, now they're going to do the classification, in which like we're going to find out the take the decision that the something will fall in which category. Let's say I have multiple features are there, and then we have the multiple features are there. So we'll calculate all distance here to here, here to here, and we'll take three KNN, 1, 2, 3. If the all three have the same like output, will going to majority vote. Will explain to you how it will look like and all. So in this also like KNN is actually to predict the most frequent class among the whole class and all. First we're going to training the that methods. We'll find out the K, how many Ks we are going to take, like how many neighboring point we are going to take. We'll take K is equal to 2, so 2 points K is equal to 3, 3 point K is equal to 5, 5 points we'll take in that from here, all data set. That we have the some 1,000 data sets are there. From that we'll take K is equal to 5, K20, K50, K70. It depends upon the how many data points we're going to take it out and all. In that also, which one is the frequent class? That let's say this is going to binary classification, either yes or no, yes, no, yes, no. So between these two, if it is yes, yes, so yes going to take decision, no, no. If we have the three, so yes, yes, no, yes, no, yes, or maybe no, no, yes, or no, no, no. So we have the majority of the two, so that the predicted class will be the yes. If we have the again we have the two, again the class will be the yes. We have the again, so it will be based upon the like called majority. That will also see. Okay. So we're going to find out the how k nearest neighbor. It's called distance between the point 1 and point 2, it's again will be the x2 minus x1 whole square. Again, y2 minus y1 whole square will be having multiple points also. We can see x, y, g also. No issue. But mostly KNN mostly will be going with the deal with the second dimension, 2D itself and all. So average of the k points more reliable when noise in the attributes are there, noise in the class levels are there, classes partially overlap. So in that we have to get the average of the k points at all. So that how to choose the k, that I said k we can take 1, k is equal to 3, k we can 5 we can take, but what will be the optimal number? So if we have the large k, we can take less sensitive to noise. We don't have much of noise, so we can take the large value of the k. We can make the decision. If we have the actual data set and some data set like it seems to be noise, so in that case we should not go for the higher number of the k. We have to go for the small k value. Better probability estimates for the discrete class, like it's something we have already well separable, or we can separately, like it's a discrete class is already there. Then we have the a larger training set, like we have the bunch number of the data, bunch number of the data will be there. So in that case, that we can go for the large value of the k. If we have the capture the fine structure of the problem space better, like it's a bit of complexity or some complications are there, so we can go with the small k. Maybe necessary with the small training sets and all. That let's say I took some 50 example training data set, so we can go for the 5 also, or we can go for the 2 also, 3 also. It will give the better results also. So again, we have to make the balance must between the structure that the large and a small k value. So as the training set approach the infinited, k will go into large. Then so it will KNN will become the base optimal. It's based upon the Bayes theorem. Like it's a probability based. Okay. So this is the how the KNN will look like. So I think we can go with the something called code for this also. Again, I said like this is the things first instance or maybe the classical KNN. Whenever we'll be having some sort of data imbalance and some sort of overfitting or biases will be there, so we have to go with the weighted like also. So class will be there, then we can assign some weights. We can do the predictions. So we'll be having the data set. If there is some sort of data imbalance or some other things will be coming into the picture, so we can assign the weight to the class, and then we can do the predictions. So it's actually to deal with that. It's to something do the optimization to prevent overfitting or maybe the underfitting also. Okay, this is how it will go. So in that also we can give the weight two types: distance weighted KNN, locally weighted KNN also we can give. So it will not go much of detail of this. Okay, will not go much of detail of this. Just 1 minute. Okay, then after we can do in the case of like regression also. And again, I said like it is based on the Euclidean distance. Euclidean distance, how it's going to find out? Like we have the one data point, two data point, we can get 1, 2, and then this is we can get the value. So given all attributes are the equal weights, if scales of the attributes and difference are the similar. So this is the actually that the limitations for the case of the KNN and all. KNN actually we said it's very classical technique. We have that now people are using the ANN and CNN also. and another like various like reinforcement learning also, maybe the in symbol methods also where people are using and all. And here also we're going to make the spherical classes and all that will be there. Then again, say same way we can do the weighted Euclidean distance, like one have distance between the two have the too much far will be there, so we can do the weighted also. That the large weight we can give, then the attribute is going to more important. That the small weight when the attribute is going to less important. So it's actually what they will do, like weights allow KNN to be effective with the axis parallel to the elliptical axis, like when they're going to create a one plane and then hyperplane. So it's going to have like clear separable line we can see around and all. Okay. So then we'll be having a curse of dimensionality. If we have the number of dimensions are more, what will happen? Whenever we have the features are there, we'll be having a as the number dimension integer, distance between the point will become larger, more uniform, and if numbers of the relevant is fixed, increasing the number of less relevant attribute may swap the distance. Like what's happened when the dimension will be having more, like so there will be a complexity will going to increase. So when more irrelevant than relevant dimensions, so distance become the less like reliable. So in that case, we have to reduce the dimensionality. For that, what we have is the PCA and LDA. That's also we'll see. Before going to the PCA and LDA, we'll say the KNN codes also. Okay. So again, the KNN things, what they will do, we are going to class A, class B is there. Based on the distance, we have this is the unseen data. This is the data you was used for training. Now from this we'll find out this one, this one, this one, this one, this one. So we can see for this point 1, 2, 3 is the class A, and then for this point 1, 2 is the class B. So if we take the majority, so it comes class A. So this is how the things will work in the KNN. I think that concepts are clear now, or I am going a bit of fast.
No, sir, clear.
It's clear,
Yeah, yes.
Okay, so now we'll see some problem again with the similar example I'm taking. Just say like I'm taking the similar example so that so the things will be clear. The same concept and all. And again, I'm saying this is not some advanced problem. It's a very basic problem. Just to have fundamental clears. The same thing that you can apply in the case of like that real time, it's like that applications also. I'll show one papers and all, that's how it went and all that. So that's also I'll show to you in the last, but not now. So the thing is that our that agenda is to not to solve some very complicated problems and all. There are people are working on this like in 6 year, like 6 months, or 1 month or 2 months. So here are the things that our fundamentals should be clear so that we can apply into the real time application. So now we'll go to the like we have the again similar problems are there. We want to classify the student into the two category: good performance, that's called bad performance, based on the how many hours they have studied and what was the corresponding attendance. So in the input, we are having one is the number of hours, second what we have is the attendance, and then for this the target value is the class, either poor or good. Okay, so this is the whole agenda of the problem. The same thing that you can apply in your class also. If any faculties are there, they can also apply the how your class is going to perform in the coming examinations and all. That's how the things will work. If you want to automate the like full classrooms and all. So now we want to check if a student have a study for the 3.2 hour, they have the attendance of 76, like 76%. What will be the predictions, either good or poor? The things is that what now. So if you see here, we are having the KNN actually stands for the K nearest neighbors. Nearest, then neighbors. Neighbors is something one place, two place, then how close are there. This is how things will work for the KNN. So we find the three closest student. Good, good, poor. Then majority will be going to vote then it becomes the good class. Okay. This is how things will going to work it out. So that let's say we have some examples are the study hour 1 to 6 hour. Attendance is the approximately 50 to 95%. In that case, we have to do the Z score normalization. It will come into the data pre-processing. Before that, before the normalization, we have to do the data cleansing, we can say. Let's say for my case, I have the data of the signal of the muscles or ECG data is there. So I need to remove the like power line or maybe the inference line, or maybe it can be any sort of noise will be there. So that I'll do the data cleansing. Once data got cleaned, for some participants, for my case, the data is for the 1 minute. For second participants, that we have data for the 2 minutes. So for that to become on a same scale, we have to do the normalization. Once the data got normalized, we can get the feature. Once the feature we got, then we'll feed to the training, then evaluation, then prediction. This is how the things will go. It's like first step to data, it's the raw data. First step, data cleansing, and then data pre-processing. If you want to do something like some in the data cleansing, only pre-processing will comes into the picture. Then we'll be having the feature. Either the feature itself we have, or we have to extract the feature. Let's say I have the voltage versus time feature, like signals are there. So I have to calculate the frequency, maybe the RMS value, or maybe I have to calculate the some that entropy value, or maybe some other feature that we have to calculate. So once we got the feature value, we can give it to the training. The training can be any model will be there. Then we can evaluate on the unseen data. Then we can make the predictions. This is how the structure of the full machine learning will going to work it out for the any of the problem. The only thing, the core of mathematics will change of any model. If it is KNN, it will go with the Euclidean distance. If it is decision tree, it will go with the entropy, in that information gain or Gini index. If it is SVM, other things will come. That's called hyperplane. If we have the regression, then other things will come into the picture. So this is the things. The core of mathematics will change, but the agenda or the methods will be same for the whole machine learning methods and all. So now we'll go with the KNN one. I have to see where is the KNN one. Okay, I'll go with the codes of the KNN. Okay, so we have the code of the KNN also. So again, what we have seen that it was the classification problem. Predict the student performance, features, study an hour. Classes were the good, either good or poor. Here again, we took the data was very less, so we have just given two for the X corresponding. We have the number of hours, attendance percentage, and then we have the target value categorical in the case of poor and good. Then we can see the how the data will going to look like. Then after we have done the standardization, like it's called Z score normalization x minus mu by sigma. If you study the like Poisson's distributions, if you are aware of that Poisson distributions, so that this will be more familiar. Okay, hopefully it will be clear. It's mostly probability and statistic things will be comes into pictures and all. So once we have done the standardization, so we can see the KNN. So here KNN, what we have is the fit. See KNN x g y. Then we have to keep the how much number of the k, and we are taking the distance of Euclidean and Euclidean. So now it's the x and y. Earlier the value was the x and y was the corresponding to the x. We were having the y. Actually, then in that case, we can't feed this value, so we have to convert into the either 1 or either 0. So we have done with the xg. So this is the normalized value. This normalized value we have given to the model. Then their target value was either poor or good. Then we have the number of the neighbors. It's called how many numbers we're going to take. K is equal to 3, K is equal to 5, K is equal to 6, and all depends upon. Then we took the distance. Which distance we have to define the Euclidean distance. Then after, if you're going to run it out, how it will look like. if you're going to run it out, this is how the data is going to look like. And if you go to see for the decision region, how it took like it, this is the yellow is the poor decision and the blue is the good decision. And we took the data, new data is that they have studied for the 3.2 hour and 76% of the attendance. So what is the predictions? Then this one we know the model, we already trained it. This is actually for the normal that new data. For the case of new student, study hour was the 3.2 hour and attendance was the 76%. So they got the good marks. If we go to the number of hours is equal to 1.2 and attendance will be the 46%, we can see how it will look like. They got fail, means it's a poor. We can see here they are in the category of here, not in the good reason. Okay, so this is how the things will look like for the predictions. Again, we can check with the decision regions also, like up to what extent it's the in the good decision, in the bad decision. We can check it out. Like this is the boundary they created. Like this is the boundary. Above of all, it's a good decision. Like it's a good decision, a reason that anything in this reason, even they will study for the 1 hour or 0.6 hour. If they have the attendance of 91%, they so they're going to good student. If they have studied for the even for the 5 hour, but the attendance is having 52%, it means it's a very like it's in the bad category. Okay. So then after what we can go, we can do the again in the train test split also. Instead of training on the full data, we can divide into 70 or 30% case. We can get the accuracy also, and then we can get the confusion matrix also. This is how the things will look like. This is how the confusion matrix will look like. There is no case of false positive or false like that negative. So it's a we got the test accuracy of the 100%. Okay. So I think with this the KNN is clear. Shall I go with the next one?
Yes, sir.
Yes, sir.
One more code we'll take. We'll be having KNN with the different K. Earlier we took the first K. Now we can see the if we take the K value of the 135, how it will look like. So again, it will things will be same. We have converted into the standardization, like it's called normalization. K value we took the 135. So we're going to give the for loop. First we'll take the 1, then second we'll take the 3, then 5, then we're going to fit the model. For loop we took why? Because we have to we're going to run the loop. First they will do for the first k is equal to 1, then second they will take the k is equal to 3, then the k is equal to 5, then we'll get the similar way we can get the all other things will be there. So if we're going to run it out, this is how it will look like. This is going to k is equal to 1 like a reason, then k is equal to 3 reason, then k is equal to 5 reason, then and then one more things will be there. What will be the optimum value? K value 1 to 15 with the spacing of 2. We'll be going to check it out. So what will be the optimum value? So we can do the fit model fit of C KNN based on that, and then we can get the here. We can see here. So after that, it's going to flat. So optimum K value is the 5. We have the 100 like 0 KNN, and then we got the test accuracy was like once after some certain 3, it got drop like drop to 66%. So then from here it becomes the flat. So we have the optimum value of the K is equal to either 5 or 3. We can take it out. So we can find out the what will be the optimum value, because sometimes this data set is having very low number. So we can K equal to 3, K equal to 5. But if we have the data set of like 1,000, 2,000 or maybe 10,000 and all, So we have to find out what is the optimum K value and all we can see out on. I think we can go to the next part now. Next part is that what we have is the feature reduction. It's called dimensionality reductions, we can say and all. Okay. So it will be the whenever we'll be having a too many like number of features and data sets set will be there, so will be that the model will get confused. Either we have to get the more informative feature. Sometimes some feature will be the very dummy. Sometimes that the height and weight, or maybe that height and width will give the same constraint context as compared to the like some other parameters and all. So in that case, either we can remove the width or maybe the height because the same will get. So that's the thing. So whenever like it's something will be giving, will try to give the like machine learning model like to some informative feature, not the very unnecessary data and all. So the information about the target class is inherent into the variables. It all target class will depends upon the like variables itself. Okay. So if we see the like more features, more information, more discriminative power. But the thing is that we're not going to use more and more feature. We'll try to keep as minimum as possible. So that's why we have the feature reduction techniques. Let's say we have that like PCA, LDA, what they're trying to do, they're going to remove unnecessary feature and all. I'll show one paper actually how they have done it, like how it's my paper only. We took somewhere 14 data set. So this is that recently we published actually. In that what we have done, we have took the somewhere around. Let's see. I'll just explain. We have collected the data. Once the data was acquired, we have done the pre-processing. Then we calculated some features, and then we have done the feature selection. For that, what we have used the PCA and GA. PCA is the principal component analysis. GA we have used for the genetic algorithm, and then we have whatever the feature was selected, we have given to the decision tree, SVM, then a random forest, and then ANN was given. So now I'll say feature reduction technique like where it went. Feature extractions and selection. So what we have done, following the just 1 minute. We took the total of 30 like a 13 dimensional feature, so that the PCA took how many first 9 particular component was taken into the consideration. So the thing is that based upon that we are having this value where it went. This is the 9 feature we are having. This is the 13 feature we took for our study through the PCA. Through the PCA, we have taken the somewhere 9 feature, and through the GA genetic algorithm, we took somewhere around 7 feature, and then we have done the parametric study. How it will look like, I'll show you. Classification performance with the all feature. Once we took the all feature, like for all 13 features, we got somewhere around 92% of the result. Then second case, classification performance with the using PCA, we got like 96.5 like 58 percentage, like that the performance got increased. Then we have compared with the features selected using GA genetic algorithm, so we can see 96.62%. It means whenever we are trying to reduce the feature or just see reducing the feature, it's not about the eliminating the data or anything the information. We are trying to reduce the irrelevant feature, reduce the non-informative feature to the model, and then that's what the things will come into. Otherwise, what will happen, that the computational time will get increased, that the model will going to take too much time to train, then that we need a more sophisticated system, like very big system we need and all, and sometimes we will not get the better results also. Either it will going to get the bias or some it not going to generalize properly and all. So this is the whole case and all. So what will happen? Classification performance. It was number was less, number of variable. It was low. It got increased and peaked it here. Let's say it was the k is equal to one. Feature was the variable was the one. Here 7. But after 7, 8, 9, 10, what happened? That the classification or the performance got decreased. The thing is that's why whenever we'll go for anything, we should not go for the match too many features we want. Let's say I want to go for the with the bikes. In the bikes, what we have, they are giving them too many features are there. Traction control, cruise control, this feature, the part feature in this. So in that case, to keep the pricing in the check, they're going to play with the engine capacity or the mileage and all. So what will happen that the performance is going to degrade, but we have the more feature. So that's why we have to make the balance between the features and the performance also. That's why I am the big fan of the Honda. They're not much into the feature, but they are more reliable, or even we can say they are much they're giving a much better performance and all. So the same thing will happen in the machine learning also. Okay. So I think this is that. So that now we are clear with the case of what I can say, feature reduction in the machine learning. It's clear now. Can someone tell? Feature reduction is clear. Now we'll go with the PCA and
Yes, sir.
LDA. So then after what we're going to do is that irrelevant feature or maybe the redundant feature can confuse the learner, and they're going to, when we have the limited training data, so it's going to computational resources will be there. So then it will become the dimensionality, more dimension will become the curves for the model. So in that case, we can do the feature selections. It's based upon the different PCA method, or maybe we can do with the genetic algorithm, LDA methods, we can go with that. So now we'll go with we have the x vector are there. We can calculate into the x feature selection based upon the some scoring functions, like maybe the variability, or maybe some we can calculate the subset of the features and all. Then we can give into the that the machine learning model. So what will go search the what is the feature selection steps, data training, search feature subset. Goodness is this. We can go then objective functions. We can final feature subset. Then we can give it to the algorithm. In the case of PCA, we're going to take 95% of the variability variance. If some features have the more than 95% like that the variance, we're going to take the feature PC1. If we have the second one PC2, 3, and then similarly, then we can take 70% of the case, we can take this data, then we can feed to the our but I can say that the machine learning model. In the LDA case, we have to find out the discriminant, like test the how much differentiable the things will be there and all. So in that case, if once they're going to do the search, we have the different methods of the optimum search, heuristic search, randomized search will be there based upon their similarity. Then we can check with the how can we evaluate. We can do with the filter method or maybe the wrapper method. Filter method also we can do the user based or maybe the item based. Then we can do the how can we do the evaluation, supervised case, training use the subset. Then we can find out the estimate the error. Unsupervised we can do with the filter methods and all. I think then what we have for the regression, will be having the one more coefficient, Pearson correlation coefficient. It's called how strongly correlation is there from the one variable to the second variable. We can see is if it is rho is equal to -1, we can see there is no correlation. Then we have the 1, 2, then +1. If the perfect, also we can get it and all. So it's a when we have the lower R value or rho value, so it means it's giving it's not perfectly correlate. it means like they have the variability or they don't have the some, it's like a similarity and all. Then again we can check based upon the signal to like a signal to noise ratio. So in that case, signal to noise ratio SN ratio should be high. Means that noise should be low, signal should be high in the any cases. Then we can do the multivariate feature selections also. We can do the multiple feature we can select and all. Now we'll come to the PCA. PCA, what we're going to do, they're going to generate a hyperplane, but then we can calculate the correlation between this and this. We can calculate. And if you see the algebraic, so variance of z should be the maximum. Okay, so means there should be a variance between the two variables. It should be a maximum case should be there. So now then we can calculate the based upon the principal comment 1, PC2. We have the one feature, second feature. We can calculate the based upon the like this 1 point their variance. There also we can calculate the Z2 feature. So this PC1 will be having more variance than PC2. PC2 means PC1, PC1 and all. So choose the direction such that the total variance of the like the feature will be the maximum. It's called maximum total variance. Choose the direction that are orthogonal, and there should be like condition is that both vector or both features should have the orthogonal. Means variance will be the maximum, but the correlation should be minimum. Okay. So if someone asks what is the principle of the PCA, we should get the maximum variance, minimum correlation. Now, oh sorry, we'll go back. Where is that? Okay. So now the things how it will look like. First principal component, second component. In the last, how we can see out original image, it will look like this. So this is the things like how it will go. This is the original image. Then first component, second component, and once we do the that the compression. This is the original image. Once we do the compression, it will look like means we have the much less number of features are there and all. So is PCA is the good criteria for the classification? Yeah, it can be. It will give sometime better perfect classification, but sometime we're going to miss the class informations also. So what is a good projection? Two class overlap or maybe, and that it should be able to what I can say separating different class and all. Now we'll see some example. So now the thing is that we have the 5 original feature. We'll try to read the 2-dimensional features. So x 5 dimension to the x 2 dimension. That is the purpose of PCA using maximum variance and then minimum correlation means that each other vector should be orthogonal. Okay. So now we'll take again one example. Now we are going to find out the can we represent the data using fewer dimensions while retaining the most of the information. The thing is that we have the one total of 8 students are there. Study hour 2, attendance is there, assignment is there, midterm is there, previous score is there. So now we have to see like how we can represent the same things with the minimum number of data set and all. So what they will do, PC creates the PC1, PC2, PC3. Variance of the PC1 will be the high, maximum possible variance. Then second, then third, and so on it will go. Then what they're going to do, they're going to find out the center of the data. X and mu, it's the mean of the like each feature. Then calculate the covariance. Covariance when it tells how variable vary going to together. So then after they're going to calculate the eigenvalue problem. It's again the algebra. So that's why don't directly jump into the machine learning. You should have some idea of like algebra and the statistic and all to understand better of the machine learning problem. So now we'll go with the PCA code. We'll show it to you. We'll come here. We have the one more code PCA. the things are again same. We are having the 5 academic feature into the 4 dimension, and we have to retain the maximum variance. The data is we have the 5 features are there, number of hours, marks, and then other things will be there. Then after, features names are there, study hour, attendance, assignment, midterm, previous score. We have to do the standardize, like we using the Z score normalization. Now we have to do the PCA using the feature of PCA XZ, like it's the coefficient value score, latent value explained. Then for this, what we have the code PCA of XZ. So to get the Python, like we have the PCA. We can see here how it look like. PCA of whatever dimensions are there. We can see the scalar fit or not. Here the things initialize and fit the PCA. So here from 5 feature to the 2 component, they have taken from the is equal to 2. But here what we have done, like what we have simply we took KNN. So now we will be able to then we can see the display the results, how it look like principal component loading, then variance are there. Then we can calculate the cumulative variance also. Then we can see the variance plot also. It's just a way to see actually. Then reduce to 2 dimension. In that case, x we could reduce to the score 1 to 2. Okay. Then after PCA 2D visualization we can also see, even 3D also. Now we'll be seeing how it look like. We can see here. This is the PCA variance experiment. First component have the 100% variance. Then second, third, fourth, we don't have much of variance. So it means perfect value. We can say cumulative variance, only one features are having like much higher. Then how it went from PCA projection from the 5D to 2D, we can see here, like 5 dimension to the 2 dimension, first component, second component and all. Then this is how it look like, PC1, PC2, that loading and all. And we can see the numbers also here. First feature, second feature, third feature, fourth and fifth feature, we can see how much variances were there. And we can see the variance explained. First have like variance of the 99%, second, third having the minimal number of the variances are there, and so on. So this is how it look like to the PCA. I think the PCA part is that clear now. PCA we have to see the 2 part only. Variance should be the maximum, and then correlation should be the minimum. That should be a orthogonal vector. So this is how the PCA. I think that with this the PCA will be going to end. So now next is the then again we'll be having what class of information may be useful. Again we'll be having based upon the centroid, based upon the class, or it depends upon. Then we can get the LDA also. LDA finds out the most discriminant projection by the maximizing the between class distance or minimizing the within class distance and all. So PCA, 1 feature, 2 feature, in that variance was the maximum, and then correlation should be the minimum. Variance maximum, correlation was the minimum, but here within the 2 feature, maximizing the between the class distance, like yes and no. So they're going to maximize the distance and then minimize the yes distance or no distance. So this is the principle for the case of what I can say LDA. Okay. So again we'll see in the same cases how it will look like. We have the 2 features are there, then 3 classes. Then we have to find out whether how it look like for the particular 3.8 of 76% and all. So I think the same way, large between the class separation, small within the class variations. This is the formula to get the things. Again, we'll not go much of detail of this. and then they're going to between class scatter, within class scatter, they're going to maximize. Between the class scatter, it should be a maximum, it should be a minimum. So overall, it's become maximum. So if you see the PCA, it's unsupervised. We have the supervised machine. So in the PCA, we are not going to use the label, but they're going to use the label. Here, like maximum, that maximize the variance. Here, maximize the class separation. Useful for the dimensionality reduction. Useful for the classification or discriminant projection. Here, maximum principal component will be having the less than or equal to the number of the feature. Here, maximum in discriminant feature will be the if the number of feature is C, so we can get the maximum number of discriminant, will get the C minus 1. Okay, so this is how the things will look like for the LDA. So I think we'll see the course of the LDA also, and with this we'll end for the club today. Okay, so again we have the two features, but we have the three class. It's called multi-class classification. It's not the binary class classification. It's a multi-class class classification. We have the two data set. We have the three category, and then we can first we're going to visualize the data. Then second will be fit C discriminant. For the PCA, we have the just PCA of the XY or XG like that will be the normalized value. Here, fit discriminant of the X and Y. Then we can check on the the new student also. Then we can see the where it is going to make the decision, and then we can again go with the train and test split set also. We can calculate the accuracy, confusion matrix, and so on. If we see going to run it out, how it will look like. So how the data would look like? Data was for the 1 hour this much mark and all. It was there. How they're going to make the decision? Just see. This is the poor decision, good good reason. This is the average reason, and the data set we have took 3.8 hour, 76% and that attendance. It came to the average, and then we got the confusion matrix also. It's 33.33%. It's not the good results actually. So I think with this we can stop the lecture today. We have some more data set
Sir, I have one question. The genetic algorithm is used for feature selection.
that we can use it out. That we can use actually.
Okay, sir. Just PCA used for feature reduction. Then genetic algorithm is also used for that purpose or someone else purpose.
Actually, genetic algorithm is actually optimization technique. Optimization technique. It works on the brain network and all, and it's works on the mutation, and it's called optimization technique. So whenever they will try to optimize the feature. So that's why PCA, it was something we can select the all feature, but we took some some random feature like that 9 feature, but GA were able to give for that particular mutation this much of the feature was relevant to the our that study, so that we can use also for the feature selection also.
Okay, sir.
Yeah. So
Evaluation. वो क्या कहते हैं in biology वो क्या कहते हैं evolution के लिए कहते हैं human evaluation.
Yeah. So that's what
Okay.
it's called mutation. It will going to evolve.
Okay, sir. Thank you.
Then tomorrow, first, next class we'll start with the how it will go into KNN and all. So we have this -1 and 1. So let's say first point 1, -1 and 1, and we have the target point is the 1 and 1. We'll calculate the Euclidean distance. Okay. So let's say 1 minus 1, 2 square minus 0. So it came 2. So for this, what we have is the class is the minus class is there. So now 0 and 1, 1 and 1. So 1 minus 0, 1, 0 square. So we got 1. For this, what we have is the positive class. Is it? Then, so similarly, we'll calculate for the whole point. Similarly, we'll calculate for the whole point. So here we got how much value? 2. We got the value of 1. Here we got how much? Anyone can tell? 1 minus 0, 1 plus 1 minus 2, it's called root 2. Is it? And here 1 minus 1, 0. 1 minus 1, 2. It came 2. Then after 1 minus 1, 0. And then it came 1. 1 minus 1, 0. 1 minus 1 came, it came 1. 2 minus 1, 1. So it came 2 minus 1, 1 plus 2 minus 1, 1. It came root under 2. 1 minus 2, 1 plus 2. Let's say 4. It's a theoretical. So now we have to see like input class variable dependent variable. Euclidean distance for the KNN 3NN. So means K is equal to 3. So we'll take minimum 1, 1, 1, and then one more 1. So 1, 1, 1. We are having like class of positive, positive, and then we don't have the negative. So that 1, 1 will become the positive class. Okay. I think it's clear. No, it's the manual way to do how we can find it out and all. It's clear or not clear? Just tell me.
Yeah, it's clear.
Okay. So now we have the second part is that we have the 10 classes there. How that how much number of the recommended bill can get? C minus 1. 10 minus 1 is equal to 9. It's clear? So C is the option. Then K nearest neighbor is the algorithm. Which one is that? It's not the eager. It's non-parametric. It's not the parametric. It's not the eager. So this can't be. This is the non-parametric. This is lazy. Like they're not much worry about like they're going to manual way and all. So this is actually a non-parametric and lazy algorithm actually.
So what is the difference between parametric and non-parametric?
KNN is actually, if you see, like parametric is something like they're going to, what I can say, it mostly will going to depends upon some parameters. Parametric is something like based upon the one things will change the others also. But here KNN it's going to one parameter like it's going to Euclidean distance also, one Euclidean distance, and they'll try to minimize here. So this is things like non-parametric. How can I say like it not externally influenced by the some factor and all. Okay,
मतलब hyperparameters you are talking about.
we can say, or maybe the
Okay.
other influence, or maybe the external source we can say. There is still that like doubt is there.
No. Sir.
Okay. So it's not going to assume the specific or fixed function that like they don't have. If something fixed features and all will be there, so it's called parametric. Based upon the parameter, you're going to make decisions. If they don't have, like it's the random way we can go. So that's called non-parametric. If we have something based upon some features, it's going to stick with the probability, like that. The based on the probability or something, it's called parametric studies and all. Okay. So we can go with the another one. Which of the following statement is true about the KNN algorithm? So KNN actually they do more on the test time rather than the train time. Why? Because they are trying to find out the distance all that we can say, because it's the lazy learning platform. So they're not going to, they'll be more on the test platform rather than the train platform and all. Okay. So when like a new test point will arrive, KNN has to find out the distance. Okay. For the many points, they'll find out the neighbors, then perform the majority. So in that case, but so they will going to take more time on the testing instead of training itself. Okay, so we'll go next one. Which of the following necessities reduce feature reduction in the machine learning? So they are going to like necessities is the that irrelevant and redundant feature. It's good, like it's the correct only. And then curse of dimensionality, they're going to reduce the performance. Then we we have the limited computational data resources. So it's all of the above. Now next, just tell me when there is a noise in the data, which of the following options should improve the performance of the current algorithm? Just tell.
Sir, large K.
Okay. So if we increase the K, so we are going to make some more distance. So it's going to be a large K value. And this is the actual value. We can calculate the formula. R is equal to summation of x minus xi into y minus yi root under summation of x minus x bar. It's actually a x bar actually. Xi. Okay. So first you calculate the x bar, then we calculate the y bar. Okay. Then calculate the x minus x bar, y minus y bar. Then do the summation for the whole cases. Then multiply it. Then put the formula. We'll get the value. So I think that you can do in the like at home also. I think there's nothing to explain. Is it?
Yes, sir.
Which of the following is false about the PCA?
Sir, PCA is supervised method.
Yeah.
It is unsupervised actually.
It's actually a unsupervised method. I think the time we have already crossed. Okay, one more question will be there. In user-based collaborative filter-based recommendation, the items are recommended based upon the users. Is it? It's user-based means users one. I like a similar item, so it's going to be a item-based. Then the next what we have is the PCA can be used for the projecting the and visualizing data in the lower dimensions. Yeah, true. Is it? Okay, so that's all for today. So shall we wind up?